All right. So good morning again to all of you. I would like to start by making some comments about the grades that I posted yesterday, and I hope that you have seen my email. Primarily, you all know your grades because they come out automatically to you through each one of you receives your own grades from both TabHat and eCampus. However, what I did is that I put on an Excel file everybody's grades, but of course you can only identify your own if you know your university ID, your student ID. And you can see, in fact, how the grades distribute, and also specifically how the bonus points have been given away to individuals on the basis of what we had discussed. I made some changes to the small changes to the bonus grade points, but I have to tell you that I only increased points. I try to do that just to simplify things. I have not necessarily changed or reduced points for bonus. I made a few increases here and there. And also, I made some changes on the number of expected additional exercises, quizzes, and homework. Because as you know, we had some disruptions in this semester. And of course, in the beginning, when we publish the syllabus, every faculty member makes the best possible guess or assumptions about how the semester will run and how many of each one of those we will have. But obviously, as you can imagine, there are unexpected events like we had this year, or even some changes that the instructor may choose to make during the semester. So in any case, you can see the total number of exercises, the total number of quizzes, homework, and of course we have the midterm. I have not included the makeup exam because this is only for those that have missed points with valid reasons. I have received so far the names of 5 individuals who will take the makeup exam, and I'm gonna give it out this weekend, as I mentioned, this Sunday, this coming one. So in any case, I decided to show how I distributed the bonus points, because I'm sure many of you would have many questions, and instead of responding to each one of your questions individually, I tried to do the best I could. So it's there for you to see. And one thing that I wanted to mention to you, and I believe I have done this both on my email and announcement, and also I have included on the website the eCampus file that I have created for this to explain the bonus system. I have given you bonus points, so in the form of a bronze star, silver star, and gold star. And I have done this on the basis of the maximum points that anyone could accumulate as of yesterday. And so these are not the total points that you could accumulate for this class, but just what we had as of yesterday. What that means is that if you continue along the same path without changes, of course, you're going to keep those bonus points until the end of the class, and those will be calculated as part of your final total number of points for the semester. However, if you do better than this, you can, or those of you who are close to getting some additional points, you can do that. And you can see how close you are or you are not, or what you need to do. You have all the data in front of you. At the same time, if you choose not to continue with the progress that you have made so far, and you lose your status, then I will take away those bonus points at the end of the class. I have given them to you now, assuming, so you see exactly, you have a good picture of where you are. But as I explained, exactly how this is going to work throughout the semester. We have only 2.5 weeks from now at maximum, at most. In any case, if you have any additional questions, you can join me during office hours, and we can discuss your own case separately. All right, so today we are going to start with the Smith chart. I called this week, the title is Introduction to Smith chart, because of course we don't have enough time to become experts on how to use it. You can also find a lot of information on the internet about the Smith chart, and the picture that you see in front of you, I just downloaded. It's a very clear PDF file that I found and I have used over the years. It is on the internet. You can find it. You can copy the one that I have, which you're going to find also in my notes, or you can use another one. There are so many different ones. There are some that are extremely complex. I try to use the one that is the most standard, in the most standard form. And you can use this one, as a matter of fact, to solve any problems. It's the definition, the resolution is extremely good, so you can zoom in and you can read very clearly the numbers. It's a very busy chart. It has a lot of information there. And so we are going to start learning about it. We are not going to become experts in solving or designing complex problems, but we will know enough so you can recognize it in the future. And if you want to use it more, online, of course, not on paper form anymore, you will have the opportunity to do that, and you are going to be familiar enough to be able to do some things on your own, even if you have to later. So why we have the Smith chart? Many years back, as you can imagine, people could design very complex communication systems even before the computer existed. And we were able to do that by using approximate methods for a lot of different things. A lot of the material that we are learning today was developed before the Second World War, primarily for that reason, to be able to give us easy ways to design fairly complex systems. Of course, at the same time, you may ask, well, why do we learn those things today? It's because by learning all of the concepts that we've covered in this class, we develop what we call an engineering intuition. Intuition is developed on the basis, for scientists and engineers, is developed on the basis of data and on the basis of your experience in solving the specific types of problems. Intuition is not a feeling. It's like rather the ability of our brain to synthesize fairly large amounts of information and to give us the ability to make some very important decisions without necessarily having gone through fairly extensive calculations. But to be able to develop this kind of engineering intuition, which is extremely important for designers, you need to work through concepts that were developed long time ago, even if you are not going to use them the way that people used them at that time, because now we have the computers. What that means is, if you had all kinds of computer problems available, computer software, I should say, available to you today, and you could, for example, give a direction to a computer to solve, to design a particular problem for you successfully, you would be able to design that problem, but you yourself would not have any idea on how this problem was solved. And if you were to make a quick decision about a design, you would not be able to do that. You would have always to rely on a computer to give you an answer. And an answer is as good as the software that you're using or the assumptions that have been made in the software you're using. So if you don't have an intuition, any answer will be a good answer for you. And as we know, a lot of times, not all answers are good. So in any case, for a designer, it is extremely important to have an intuition. This design intuition is not based on feelings, but on data, to be able to make an assessment whether out of a few possible solutions to select the one which is the best. So having said all of this, now we're going to learn about the Smith chart, and I can tell you, you will never use it on paper. You will rarely use it even, but it's going to give you a great sense of how things work on a transmission line. So you have a lot of circles, and on this chart, a lot of numbers, and we are going to look at each of those numbers or groups of numbers and learn what those show as we go through the various sections that I have identified. And we'll start today. We may not necessarily be able to finish it. We'll continue next time. So let me start with this. I will increase that so you can see it a little closer. All right, so this is what we call an impedance chart. All right, so we start primarily by showing impedances. And another thing, all of the impedances are normalized. They are normalized with respect to the characteristic impedance of the line. So all of these impedances that we are going to show here do not have ohms as units, but they are numbers. And so if you have, for example, an impedance, and let me write it here. If somebody tells you that your line is terminated on an impedance Isabel, which is 50 ohms minus J 10 ohms. And so all of this is in ohms here. Ohms. You're not going to be able to use this chart to represent your impedance unless you normalize it. And let's assume that somebody is telling you that this is normalized, your characteristic impedance on the line is 50 ohms. So a normalized impedance, Isabel, will be 1 minus J 0.2. All right? And this is a number. So you will have to normalize first and then use the Smith chart. Let's eliminate this for a moment. And then we are going to learn how we represent the resistive and the reactive parts of an impedance. Let's go back to the impedance, the normalized impedance we had. And we had this one. Isabel, if I remember, was 1 minus j 0.2. Okay. It has a real part, which is 1. So all of the real parts, all of the resistive components of an impedance are represented on these circles that I have shown you. So the pink one, this circle here, this circle here that you see, let me in fact see if I can show it to you. This one here corresponds to a normalized resistive part of 1. The normalized resistive part of 1 is this one down here. ZL has a normalized resistive component of 1. So any point of this pink circle, any point here, has a resistive component, is an impedance, normalized impedance with a resistive component of 1. That's the characteristic of this circle. This circle has its center along this x prime axis. It is going through point B, which is the right end of the diameter of this circle here. All of the resistive circles go through this point, and then have their center on the XX prime axis. So this one goes through 1. As a matter of fact, if I bring this closer, you will see these numbers here. You see these numbers that I can read? This is 1. This is 1.2. This is 1.4. This is 1.6 and so forth. 3, 4, 5, 10, 20, 50. So obviously the scale here is not linear. It's kind of a different scale. And it's not even logarithmic, it's something else, but it's not linear for sure. And in fact, if you go to this side of the circle, at this point is 0. Down here at A is 0. And then goes 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 7, 0.8, 0.9, 1. And then 1, 2, 1, 4, 1, 6, 1, 8, 2. And then 3. And then so this, in fact, this is 2 here. 2. Then this one is 2.2, 2.4, 2.6, or 2.8, then 3, 3.2, and so forth. It goes all the way, and this point B is at infinity. Okay, so from 0, which is here, to point B, which is there, which is infinity. Now, of course, when I have tried to do the circles using the tools that I have on the computer, I have not been able to do it extremely accurately. However, when we were using, and when I was trained on these Smith charts, we had them on paper form, and we were using a compass, and we were using a ruler. With a compass then and a ruler, you can be extremely accurate in placing your circles, and then in computing the radius of the circle so it goes through exactly the points you want the circle to go to. Unfortunately, on this screen, I did not have the luxury of doing that, so you will see some inconsistencies. All right, so the circle that corresponds to 1 normalized is the pink one. Then if you, another example is the circle that corresponds to normalized resistive load of 0.4, which is here, and up here, and it's the green one that goes here. And then the circle that corresponds to resistive part of 2.6 is the light blue and goes here. Now, let's assume that I want to, I will increase that. Let's assume that I want to create a circle that exists, that all of the points have a resistive part here, normalized, which is equal, say, to what? 1.6. Okay, then what I will do is the following. It has to go through 1.2 and 4. It has to go through this point. It has to go through B. And so if I am to write it, go like this. There. Okay, I cannot do it better than that. At this point, it will be, let me see if I can move it a little bit. Something like this. Okay, that will be then a circle that has all of the Arsabel points to be normalized at 1.6. Okay, any questions so far before I continue? I don't see any questions. All right, so now let's go and see how we represent the reactive points. You remember that we said that we had a load. Let's consider the same load, Isabel, equals 1 minus j.2. We found the circle that represents 1. Now we have to find the circle that represents the minus 0.2. Okay. Now, all of these curves, always circles. This Smith chart is made by all kinds of circles. Nothing different, not ellipses, nothing. Not a parabola, not a hyperbole, nothing. It's all circles, but they are placed differently. So now we create the y prime, which is this one, y prime and y here. This is the axis which is perpendicular to x prime. Okay, the reactive circles, as we call them, that represent now this part, the reactive part of your load, will have their centers along the y prime axis, will be tangential to the x prime axis. And in fact, here, this is x and x prime. And then we will find for each of these circles what value the points of the circle that are inside the Smith chart, not outside, inside of the Smith chart, what value they represent. So now let's increase that so we can see the details. The pink circle, which is this one, the pink circle, which is this, intersects, you see this outer line here. Let me, in fact, find a different color for you. This one. So you see this line here. This is the perimetry of this circle here. You go around. Okay, I will erase it so I can read the numbers better. But if you go along this circle, you will see one here, one. This is number 1, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2 here, 0.1, 0. And then you go 0.1, 2. In fact, it is 1.2, 1.4, 1.6, 0.8, 1.8, 2.0. And then 2.2, 2.3, 3.0, 4.0, 5.0, 6.0, 10.10, 20, 30, 50, and then infinity. So all of these points represent values on this circle. Let me, in fact, do this, the X. Okay. This is the X prime. And the value that corresponds to this is 1.2. So for the X normalized of 1.2, you have the pink circle. Okay. So this one has 1.2. Down. 1.2 here. And then 1.96 is the light blue, the circle. And as a matter of fact, you will see that all of the circles that are above the XX prime axis, they all correspond into what we call inductive loads. So all of these values that we read of here, all of these values that we read around here represent inductances. What does that really mean? That they represent positive reactive parts, not negative like the one we have here. Ours here is negative. But the upper hemisphere, our half circle, is only for inductive, as you can see from this side. And for the lower part are capacitive. Okay. So with that, I would say that in order for us to find the minus 0.2, this one here is capacitive. because of the negative j. All right, because of that. And to be able to find this, we have to go and find here 0.2 on the inner circle, which is this one. You see this 0.2? Okay. Now, in order to find the circle that goes through this 0.2, this is a huge circle because it has to go through this point here, which is the beginning of all of these circles. They are tangential to the x prime axis at this point. And I will call this point for now B, and this point here A. Okay. Now, the circle that has to go through B, and I will call this point C. This is the 0.2. It has to be as big as this one. I will try to draw it, but it's going to look like this. Something like that. Okay, not quite. Let's see whether I can move this one. In fact, it had to go through this, see? It had to go, I'll grow it. I'll grow the circle. It has to be really big for this one to go through 0.2. Let me see. Not even that will make it. Okay, one more. Kind of. It goes through. This is how big the circle is. And only the points that are inside the Smith chart will count. All right, so all of the points of this purple circle go through, assumingly, go through point C. And all of these points have a value of a capacitive value of 0.2 or minus 0.2. Any questions so far? That's how big it is. Okay, don't see any questions. Let me try to go back here. I will remove this circle for time being. Okay, and I will also remove these ones now. And what we are going to do is go to another circle and have a few examples there. Okay. We're going to go to this circle and do a few examples here. Now, before we start doing examples, there is another characteristic of this circle that I would like to point out here. And these are a new set of circles that you don't see drawn on this Smith chart, which are called the constant VSWR circles, and I will explain what that means. Okay, VSWR is a very useful parameter for transmission lines, and this parameter is defined practically as the following: the voltage standing wave ratio. That's the extensive name, which is voltage standing wave ratio. And that means the following. If I have a transmission line here, this one, assume that I have a transmission line here, like this. And assume that this line has a load at the end, is 50 ohm here, Z naught. And then at the end has a load and assume that the load normalized with respect to Z naught is 2 plus J3, okay? Now, as the voltage, and then is excited by a source for a moment, Vs. Now, in this case, we've seen that we have an incident wave, which is V0 plus e to the minus j beta z. And let's assume that this z is here, is equal 0. And then has the same line has a reflected wave because of the load. That's the reflected wave, V minus, and is V naught minus e to the j beta z. Okay, now, what do we have? We have that gamma L is ZL normalized minus 1 over ZL normalized plus 1. We have that. We have seen this. What else have we seen? That V0 plus over I0 plus, which is the equivalent constant for the current, equals Z naught. And as a matter of fact, let me write also the expressions for the current. And so here will be I plus, will be I naught plus e to the minus j beta z. And here will be I naught minus, I minus equals I naught minus e to the j beta z. Okay, what else do we have? We have that gamma at z, let's write all of this so we remember them, equals V minus over V plus. All right, and in fact, that will give V naught minus over V naught plus e to the j 2 beta z. All right, and we also know that gamma L is nothing else but V naught minus over V naught plus. Okay, so all of this is just to remind us of the formulas that we have seen in the past, and this is gamma at z equals gamma L at e to the j 2 beta z. And also, if gamma L has a magnitude gamma L and a phase, all right, because this is gamma L here. When your load is a complex number, then gamma L is going to be a complex number. It's going to have a magnitude and a phase. Okay? So from these last two, we find that gamma z has a magnitude and it has a phase term 2 beta z plus phi sub L. Okay, why are those important? Why do I write those things? Because on this transmission line, that I will write it here again, if we were to find the total voltage, the total voltage is going to be looking kind of interesting. If we therefore find total V on this line, all right, the total V on this line is going to be V of Z will be V plus of Z plus V minus of Z. All right, that's total V. And if we were to plot it for this load that we have, complex load Z sub L, this would look like something like this. Where this one is V max, V max, and this one is V min. All right, so as a matter of fact, if we were to then especially take the magnitude of this and then plot it like that, we are gonna then get rid of the phase. So it's gonna, the magnitude V is gonna have this point. All right, in this case then, we create what we call the voltage standing, this is called the voltage standing wave. Okay, so why it's called standing wave? Because that's how it stays over time. If time goes by, then the standing wave does not change, and it's called standing wave, obviously, for that reason. So now from the voltage standing wave, we define the voltage standing wave ratio, which is V max over V min. And why is that important? In fact, in most circuit designs, they don't provide the designs in terms, or the matching in terms of the reflection coefficient, but they provide the matching in terms of the voltage standing wave ratio. And the voltage standing wave ratio goes from 0, excuse me, 0, there is no 0 in this one, let me just, from 1 okay, it goes from 1. All right, how about that? Okay, got it back. This one, VSWR, goes from 1 to infinity. When V max equals V min, this line is just a straight line. For this straight line, V max equals V min. This line is straight when the magnitude of the reflection coefficient is 0. And V mean, when V mean is 0, so V max equals V mean makes the VSWR 1. V mean, when it goes to 0, makes the VSWR infinity. And in this case, the magnitude of gamma L is 1. Okay, so that happens here, and this happens there. And so when I am a designer, and I say that I have a magnitude of VSWR equals to 1, that means that I have totally matched my load to the line. But if the VSWR is bigger than 1, that implies that I have a reflection at the load. Okay. So when I try, let's see how you're gonna find the VSWR here. Transmission. We are not gonna go there yet, but I wanted to, we are not gonna read those down here yet, but what I was gonna do is the following. Let's assume that we have a load here, and I will place the load right here. It's an easy one. Let's assume that we have this point, and this point, I will write it here, is ZL normalized. Let me see what time it is. Okay, this point here is normalized, and it is equal to 1 plus J1. Why is it equal to 1? Because it's on this circle that goes through 1, and is on this circle for the reactive part that goes through 1. So this point, I placed it here. We are going to do this next time again. And then I write a circle that goes through this point. It has the center at the center of this Smith chart. So the circle goes like that. Horrible circle. Okay. This circle, I will make it next time better. If I can move it for a point, I will move everything, unfortunately, the way it is. Okay. And then I will erase everything else for the time being. So let's assume that we have this circle. Again, maybe better. Okay, this is circle. Let's assume that this circle goes through this one. This circle here has a center here, goes through this point. All right, if we then measure this length and we measure it as a in relation to the radius of this Smith chart, this radius, then whatever ratio I find, I have to measure it if I have a ruler, obviously. Whatever measure I find, which is the ratio, is going to give us the magnitude of the reflection coefficient. But also, if we go down here, As you will see here, it starts at 1, and then it goes to the right here above 1. This is a measurement of the standing wave ratio. It's called SWR here. And that gives you VSWR. So all the points of this circle have the same amplitude of the reflection coefficient or the same VSWR, which means that all of these points of the circle are these points here. They're points on this line. So if I write this circle here, then all of the points of the circle represent input impedances that I see on this line. And so we are going to continue with this next time. And we are going to start with this again and go down. I just have to tell you, you need to familiarize yourself. It's going to feel extremely confusing in the beginning. But again, there are only 3 types of circles here. They're resistive, the reactive, and the circles like the last one of the constant VSWR or the constant amplitude for the reflection coefficient. And these are the 3 circles that we're going to use to do matching circuits. But we are going to start again here at this point, and we are going to continue from here on. You're going to have, can you please scroll down? Yes. All right. We are going to explain why we have, especially about VSWR, we're going to explain that next time again. I'm going to go through and I will leave some space to make some calculations to show you why this is true. And I wanted to tell you that we have an exercise today, which is on last week's material on matching circuits, matching a circuit through a stub. And you are going to have until 6 p.m. today to do this. And please, you also have a new homework, which I uploaded last night. And please join me during office hours if you have any questions about today's lecture or anything else, any questions about your bonus points or anything else. So thank you so much. Take care.
Professor Katter, hi.
Yes, hi, Cameron.
Hi. I just wanted to ask, okay, so based on the way that the things were worded, does that mean this is the last homework, or we have one more after this?
Yes, we have the grades that I published yesterday. Did not include homework 10 because you just turned it in. And we did not have graded it. They have not included today's homework, and we are going to have one more.
Okay, so there's going to be 2 more left.
Yes, like also the grade of the homework 10. So we'll have 12 homeworks. We are going to have 5 more exercises, including today's, and we're going to have 2 more quizzes.
Okay.
In addition to the final.
Okay. I just wanted to keep track of everything. Thank you so much.
Yes, you're welcome.